Yes, thank you, Federica, for the introduction, and I also thank Jochen Glück for the invitation. Today I talk about the long-term behavior of flows in infinite networks. Okay, before we start, so that we are all on the same page, what is a metric graph? Maybe you know already what a graph is. You have a set of vertices connected by edges. And in our case, we identify each edge with a unit interval. And that becomes something that is called metric graphs. And on metric graphs, you can do usually the usual calculus. And they are also known as quantum graphs. There's a vast literature on semigroups on such structures. For example, Maeda started, I think, in 2005 together with Esther Sikolya working on these things. And people like Bayezid or Dawn or Keicher also worked on several models later. Another name is Agnes Radl, for example. She investigated something like the linearized Boltzmann equation on such networks. Another person that one should mention maybe is Delio Muniolo, who did many diffusional equations on such graphs, and also together with Federica, for example, for the square Laplacian estimates, hypercontractivity, and such things. So that's a huge theory already. And to keep the talk simple, I will assume some properties in the first place. So I want that the graph is simple, so we don't have any loops in it or multiple edges. So and also locally finite, which means like we are interested in infinite graphs in the following. So we at least have that if you watch one vertex in your graph, then this vertex has finitely many incident vertices. And we also want non-degenerate, so we have the property that each vertex has an outgoing and an incoming edge, and that are just technical assumptions. You can get around them by different techniques, but that's nothing I want to talk about here. And what we are now doing is we weight our edges in the graph. That's also something that's frequently done, and we take such weights here between 0 and 1, and we want that they sum up to 1, so we get stochastic semigroups later on. And we define this adjacency matrix of the line graph. That means we have where we encode basically our weightings. So that is usually done. And what implies that is that we get a column stochastic matrix, and the multiplication with this matrix defines a stochastic operator on the sequence space L1. So, and we have that the spectral radius is equal to the 1 and the norm also. Okay. And now I want to consider the following transport equation. In our case, we suppose that all the velocities on the mass that is distributed through the network is constantly 1. So we don't have any different velocities. We can also, if one does not have that, one can make some technical fixes for that, but I think the most easiest thing to understand is the case where all the velocities are equal to 1. So what do we have here? We have here a typical drift, one would call it, just a transport equation, and we have some initial condition that is the second here. And then we have something that is usually referred to as a generalized Kirchhoff law, that just means, okay, whenever the mass hits a vertex, then it's distributed through the outgoing edges of that vertex. And this basically means that no mass is lost in this process. Okay, and now the conference is called one parameter semigroups, so we should maybe talk about how the semigroups come into play now. For this, I consider the following state space. I take the L1 valued LP functions on the line interval, and P just from 1 to infinity. That does not really matter. The important cases, though, are the extreme cases, but you can also do that for every P between 1 and infinity. And we installed our norms or equip our spaces with these norms. So you just take the usual P norm, for example, and instead of an absolute value here, you take just a norm. So that's the usual thing you're doing on LP spaces with vector valued LP spaces. Okay, so that are our norms. And we can define the following operator. We just take the diagonal operator of the first derivative, which basically means you have a big infinite matrix, and on the diagonal you have the operators. And for our definition, for our domain of the operator, we just take the Sobolev functions that satisfy this boundary condition. So everything that's going from 1 in is equal to this thing there. And the transport equation I showed prior to that is then equivalent to this abstract Cauchy problem here. So this is our setting. And now one can discuss the semigroups generated by this operator. So in 2008, Britta Dorn proved that the abstract Cauchy problem is well posed on this L1 valued L1 space. And she also proved that A generates a substochastic semigroup on the space, which is just contractive positive semigroup, if you don't know that term. Okay, and then Christian Budde and Marieta Kramer-Fivias with another setting. They considered the equation on that L1 valued L infinity space, and they proved that it is well posed in a certain sense, not in the sense of strongly continuous semigroups, but in a sense of bicontinuous semigroups. That's like a concept with where you have another topology come into play. And they proved that A generates a substochastic semigroup on this space here. So that was the start point. In both cases, you can really give a formula for the semigroup generated by A. And that's basically just a shift, but you have a jump induced by the adjacency matrix. So that here's basically the information how the mass is distributed in the vertices. And now Britta Dorn proved the following theorem. So she investigated the asymptotic behavior of the semigroup generated by the operator A. And she proved if B is quasi-compact, what means basically that it has less than distance to 1 to a compact operator. And if it's irreducible, then you get a decomposition of your space into a sublattice, X1, where the semigroup extends to a strongly continuous positive group and periodic group in this sense. And on the other part of the space, you have exponential stability. So there, the semigroup goes to 0. All in one would call this asymptotically periodic, such a behavior, and it is common in this network business. So, and when Christian Butter and Marietta Kramer-Viersch wrote their paper, there were no asymptotic results in it. They just proved well-posedness under several different assumptions. And Dawn's result, if you go through the proof next, use of the strong continuity of the semigroup. At the one end, she applies the decomposition to the generator of the semigroup, and in the second part of the proof, she also uses a theorem from Greiner to deduce that X1 is a sublattice. So you have to come up with different ideas if you want to describe the asymptotic behavior on this L-infinity spaces. Okay, and the main observation that also Dawn used quite frequently in her proof is that if you're looking at T1, then you just have a multiplication operator with the matrix B. That is, let me go back. Yeah, if you have here T equal to 1, then N is 0, and then you have here just a multiplication operator. Okay? So how do we use that now? We can look at abstract multiplication operators, and that was something I did. So if you're starting with a bounded operator in some Banach space E, and you have a sigma finite measure space, then you can define this multiplication operator here. Okay, and if you're now looking at this map here, then you can show very easily an isometric unital algebra homomorphism, that basically follows also from theorems from Tomaszewski, that was a PhD student of Wolfgang Arendt, and the iteration there was more difficult, but we are just in the case where we have a constant multiplication here. She considered L-infinity functions, vector-valued, operator-valued functions there. Okay, so a few simple observations. M maps projections to projections. That's just because it's an algebra homomorphism. And if E is a Banach lattice, then you can easily see that the multiplication operator with T is positive if and only if the operator is positive in the first place. And you can also prove very easily that M maps strictly positive operators to strictly positive operators, which I mean positive operators that have trivial kernel. And another very important observation is the spectrum or the resolvent sets of the two operators T and MT coincide. And in this case, when you're in the resolvent set, you really have this this formula. Okay, and now I did something that I call spectral theory for multiplication operators, because if you're having spectrum here, that might be the spectrum of the operator T, and you have the same spectrum for, I have to see now, it's the same spectrum for the multiplication operator. Then you can do something if you're having like isolated parts of the spectrum. You can consider the spectral projections defined as such. Then it's a natural question, okay, the spectrum coincides for the two operators. What happens now if I look at the spectral projections accordingly? Because here you get another spectral projection Q, and here you got the spectral projection P on this isolated part of the spectrum. And it turns out that your space really decomposes nicely with respect to this spectral projections. And you can even prove that the spectral projection, the multiplication operator of the spectral projection is just the spectral projection for the multiplication operator. That basically follows from uniqueness of the spectral projection. So that is something that one has. And what you can also prove is that the point spectrum of the two operators coincide. That follows basically from the work of Rita Heimann. She also did this in a more complex setting, but that's enough for our purposes. And then you can say things about the geometric and algebraic multiplicities of eigenvalues of T. And basically, you lose information if you go to a bigger space. So that is expected. What was a little bit surprising is that if you have a pole of the resolvent of a certain order, then you also have the same pole of the same order for the multiplication operator. So that's this follows easily by the usual formulas for the residuums of the Laurent expansion. Okay, so now we have a lemma here that is the spectral theoretic core, if you want, of the arguments given in the work of Dorn. So we have a power-bounded positive irreducible operator with spectral radius equal to 1. Then if this spectral radius is a pole of the resolvent, then you know by Perron-Frobenius theory, maybe I write it down. This is just Perron-Frobenius theory is not trivial, but also not exotic, if you want. So you have this Perron-Frobenius type argument that shows that the peripheral spectrum of T consists of kth roots of the unity, and they are first order poles that follows from the power boundedness. And then if you're having a spectral projection with a decomposition, then you can, in this case, you have this decomposition, then you can easily show that if you're raising T to the kth power and restrict it to the image of the projection, then it's just the identity with just because we have kth roots here and they operate like a tuple from 1 to lambda to the power k minus 1. So this is expected. And since the peripheral spectrum contains only poles of the resolvent, you also have that the spectral radius of T, if you're restricting it to the kernel, is strictly less than 1. And the third, that is a new argument I found. You can show that the spectral projection is in the closure of the orbit of T. So if you're having a positive operator, then the spectral projection is also positive. That follows by a theorem from Weil, for example. And if you have the irreducibility of T implies then that you're not only positive, you're strictly positive. And in this case, the image of P under E is a sublattice. That's a theorem from, I think it's written in the book of Schäfer, for example. And now doing this, you can prove the following theorem. If you have a Banach lattice and you have a positive bounded semigroup on the LP space with values in E, and if you suppose that some operator in the semigroup is just a multiplication operator by a irreducible operator with spectral radius equal to 1, and if the spectral radius if that spectral radius is even a pole, then you get a strictly positive projection such that the semigroup on the image of P can be extended again to a positive periodic semigroup on some sublattice, and on the other part of your space, the semigroup is stable again. And that is basically just using that sketch of proof, maybe. You're just using that this here is just a multiplication operator, and then you can use all the things I talked about earlier to see that P is just the multiplication of Q, where Q is spectral projection on the peripheral spectrum. Of the operator B. And I called it B for a reason, because now in our application, we can reprove the theorem of Dawn, and the role of our B from the theorem, from the former theorem, is then played by this adjacency matrix, and you get exactly the same result as Dawn. So you can use this abstract multiplicational operator calculus to reprove or revisit the theorem. And what you can also do is you can extend the semigroup of Dawn to the space of L1 valued measures. And then you can show that it's weak star continuous, for example, but you also get such an asymptotic result for the extension of the semigroup. This was for finite networks done by in a paper from Esther Sikolya and Thomas Schmatrey, and but it also works for the infinite case. You just need a little bit more theory on the duality between Banach valued continuous functions and measures with values in the dual of the Banach space. Your continuous functions take their values in. And now one can also prove the same for the L infinity case, because we have seen it does really not depend on the P you're choosing. You just get this by making use of the fact that that T1 is just a multiplication operator in our case. So you can get the same asymptotic result for the semigroup of Christian Budde and Maeda Filev-Kramer. And an open problem that I couldn't solve until now is the following. quasi-compactness is a very strong restriction, because quasi-compactness of that operator there means strong connectedness of the graph, of the underlying graph. But in our case, if you just have this spectral information here, then you can show for the semigroup of the Dadorn that it's converged strongly, not in the operator norm, but strongly. And I couldn't prove the same for the L infinity case. It might be false, I don't know, but that's an open problem. But it would be interesting, in my opinion, at least. And that's all. Thanks for listening.
Thank you very much, Alexander, for this interesting talk. Are there questions, remarks?
Could I just ask something very simple?
Yes, please.
Yes, and near the end of your talk, you mentioned that the adjacency matrix B being quasi-compact is equivalent to, I think you said strongly connected.
That's wrong. This B is quasi-compact if and only if the graph has an attractor. I interchange that with irreducible. Irreducible means that the graph is strongly connected.
Okay. Well, I was about to say, because I'm not that familiar with the graph theoretic term anyway, I was about to ask what does strongly connected mean as opposed to just connected?
Connected would mean in an infinite network that your wavelength can be infinite as well. You might have two vertices that have an infinitely long path between them.
Okay.
And strong connectedness means that this path is always finite, if you want.
Okay. All right, thank you.
Some other question?
Maybe I would just comment this strong connected